this. Good. First of all, reminder, Tuesday, there's no classes at all. So, because it's Remembrance Day. And then on Thursday, you get a video only, so no lecture. My plan is to sit down and record it tomorrow. So as soon as it's done, I'll post it and you'll have it. You can watch it whenever you want. Okay. And so I'll send out an announcement once it's up and available. Which means I won't see you next week. But I hope you enjoy a little mini break from me, I guess. We worked our way through chapter 6, our final section in chapter 6. Well, any questions about that before I get into 6.4? 6.4 is our last stop in chapter 6. So we started 6.1, 1 sample proportions, 6.2, 2 sample proportions, 6.3 chi-square goodness of fit test. So it was our first time seeing a new test statistic, the chi-squared, right? So we kind of got to know the chi-squared last day. And when do we, and I guess I could do a little summary down here. 6.1 is 1 sample proportion. 6.2 is comparing 2 sample proportions. Something maybe like that. 6.3 was the chi-squared goodness of fit test. That's if you have 3 or more proportions, right? So if you have multiple categories and you have some idea of what that distribution should look like, then you can compare your observed distribution to the expected distribution, right? And so this is for 3 or more categories, which you could turn into proportions, but usually we just deal with the counts. So what's our last stop? The chi-square test of independence. Now we're going to have 2 categorical variables. And so now 2 categorical variables. And we're wondering, are they independent? Oops. Usually what that's going to look like is, or always I should say, is as a contingency table. So we've seen a contingency table before, something like this, right? And so if we have our first variable 1 here, maybe we have, I don't know, some categories A, B, C, just keeping it nice and generic. And maybe I have another variable, variable 2, with categories D, E, F, let's say G, just because they don't have to have the same number of categories. Okay. And so what you'll be looking for is a contingency table. We've seen contingency tables before. We spent a lot of time with contingency tables in chapter 3, right? Where we talked about things like how people voted and how they feel about climate change, right? We had 2 different categorical variables, each with their own number of categories, right? And so then what we might want to know is, well, how people vote and how they feel about climate change, are they independent of each other? Or is the opposite more likely to be true, that they depend on each other? And so now we'll finally have a test, a hypothesis test that lets us answer that. Okay? And we developed the gut reactions, right? You compare those proportions and you say, oh, because they're the same, right? Roughly how I would expect them to behave, right? Then I suspect that they're independent, right? Or not. But the chi-square test of independence lets you do it in a formal way. So it's still got a chi-squared, that's nice. It's just slightly different. Okay? I've got an example which I think is kind of funny. But before we do, let's bring in the section of the formula sheet that we're working on today, right? The chi-squared test for independence tells us the null hypothesis, as always. It also gives us this E calculation, which we'll use. And I'll bring this in. I'm going to paste it in here, I think. So on your formula sheet, your null hypothesis in general would be that the variables are independent of each other. Okay? And the alternative is that they're not independent of each other. Well, remember how we needed our expected counts? For the goodness of fit test, it depends on what distribution you were expecting to see, right? And so sometimes we expect an even distribution. Sometimes we expect different proportions in each category, right? And so now for a contingency table, how we calculate our expected values, right, or our expected counts, is we take the row total times the column total divided by the grand total. Okay? And so this is our kind of new way so how we calculate the expected values for a contingency table. So if I snag this, just establish some things here. So in this contingency table that we had, if you need the row total and you need the column total and you need the grand total, right, then what you would need to do first is you would need to find the totals. So you would have a row A total, row B total, and a row C total. Now down here at the bottom is the grand total. And at the bottom of each of these columns, really regretting making 4 of them now, but whatever. You would have your column D total. You would have a column E total. You would have a column F total. And you'd have a column G total. So when you need to find the expected counts, they're going to vary slightly for each cell. Okay. So when it says EIJ, all it means is for the ith row and the jth column. Okay. And so I'll clarify that here. So the expected count for the ith row, jth column. Okay. So then you would have E11, E12, E13, etc. So each of those would be slightly different unless the column and the row totals stay the same across a couple of cells. That can happen, but most likely they'll change. Okay? And so E11, for example, would be the row A total times the column D total divided by the grand total. Okay? I think it's easier to see with numbers, but just nice to see right away. Would be the row A total times the column D total, all divided by the grand total. Once you have those expected counts, then of course we will have some observed counts in each of these cells as well. So it is really messy. And if I ask you a chi-squared test of independence question on the test, I do not make you calculate all of the expected values. I'll leave like 3 of them blank that you have to fill in. Okay? So you just have to show me that you know how to do it, and then I'll give you the rest of them. The chi-squared test statistic is the same, right? From each observed value, you subtract the expected value, right? Square it and then divide by the expected value and then add them all up, right? With a big contingency table like this, that's still a lot of work. And so, and again, on the test, I'm not going to make you do that. I'm going to make you show me that you know how to find the expected counts, right? And then I would say, hey, here's a pretend the chi-squared that you found is this. And I just make it something convenient for me. I don't actually make it the true chi-squared value, usually. So sometimes I do. So you won't have to calculate it on the test, but you do need to know what to do with it. Find the p-value, for example. We know for chi-squareds, we need the degrees of freedom because the shape of the chi-squared depends on how many degrees of freedom you have, right? And so our degrees of freedom is going to be the number of rows minus 1 times the number of columns minus 1. And so in this example, right, the degrees of freedom is the number of rows minus 1 times the number of columns minus 1. Now in this example here, I have 3 rows. 3 rows. And I made 4 columns. And so in this case, my degrees of freedom would be 3 minus 1 times 4 minus 1, which is 2 times 3. So my degrees of freedom would be 6. On the test, so in real life, you have Excel or some other calculator, or you could Google and find a bigger chi-squared table. On the test, you only get this little guy. Once you have a chi-squared, though, it behaves the same way, right? We need to know the degrees of freedom, and then we can find our p-value or our critical value, right, like we did last day. Notice that I stop at 5. So this table, this contingency table is too big, right? And so because I can't give you something with 6 degrees of freedom because I don't give you the table for it, right? And so I'll highlight that there's kind of a limit to how many rows and columns I can give you. All right, so on the test, we have a maximum of 5 degrees of freedom. More degrees of freedom exists, of course, but I kind of cap it there. Which means we could easily do a 3 by 3, which is still quite large, right? 3 minus 1 times 3 minus 1 is only 4, right? That's on the table, haha, so to speak. All right, and so that's still quite a large table. Okay, all of this without any numbers. Wow, crazy. Any questions though before we introduce the example that we'll work on? Yeah. There's a data set called Popular, where students in grades 4 to 6 were asked whether good grades, athletic ability, or popularity was most important to them. A two-way table, which is a contingency table. So a two-way table, we call it a contingency table. But you can see how, right, we would call it a two-way table because there's 2 categorical variables. I should say contingency table. Separating the students by grade and by choice of most important factor is shown below. Do these data provide evidence to suggest that goals vary by grade? Right? And so really what we want to know is, okay, so these are the grades, even though the grades is one of the outcomes in the goals. Okay. But we'll call this our goals variable, and this is our grade variable. Okay. So we've got these counts, and they've got a mosaic plot, which I don't actually like because I don't think they're very helpful. And so we'll focus on the contingency table, right? And so what we want to know is there some sort of relationship between the goals and what grade the students are in, right? So let's do this instead. I was going to, I don't know if we'll have time. How do I? I want to remind you before we start what the conditions are. Oops. No. Man. Just all over the place here. Paste. So as soon as we see, do these data provide evidence that tells me I have to do a hypothesis test? Right, let's start there. When I see a contingency table, there's really only one thing that I can do with a contingency table, and that's a chi-squared test of independence. And so, and really nice about the chi-squared is we only do hypothesis testing. We don't do confidence intervals, right? Just because it's not symmetric. And so first thing we need to do is we need to check our conditions. I'll do a recall from last day because I brought this in from last day. The conditions for a chi-squared test are really simple in comparison to a 1 sample proportion test or a 2 sample proportion test, because those conditions are huge. Okay. First one is independence. Okay. Each case that contributes a count to the table must be independent of all other cases in the table. Okay. If you've randomly sampled, then you can assume that that's true, right? Another way that you could argue it is, are all outcomes disjoint, right? You can't have any overlap in any of those categories. If you're in grade 4, you can't be in grade 5 and grade 6 or anything but grade 4, right? If you're choosing your most important factor, you only get 1, right? They're all important to me. No, you have to pick your most important one. Fine. Grades, I guess. Womp womp. They're only in grade 4 and 6. Popular is probably a bad one, but sports might be nice. So, anyways, all those outcomes are disjoint. That's great. The sample size condition, each cell has to have at least 5 expected cases, which means we need to find the expected counts. So often what we do for chi-squareds is just immediately calculate all the expected counts, right? Even before you start your hypothesis test. Okay, and so here, need to find all the expected counts. And then usually, like I mentioned last day, we usually don't do this. This degrees of freedom has to be more than 1, especially in a contingency table. That's not an issue, right? But you do have to have more than 1 degree of freedom, because if your degrees of freedom is 1, right, then, well, it's really hard to get in a contingency table, but there's probably a better test that you could do instead. Okay? So usually I just skip that one, which means there are only 2 conditions that I need to check. Okay, let's go ahead, and I'm struggling because do I want to just stick to the slides? Fine, but I really struggle with it, don't I? If we have to state our hypotheses, step 1, state the hypotheses. On your formula sheet, let me go grab it, you've got this generic null hypothesis that the variables are independent. What I want you to do is make them question specific or variable specific. Grade and goals are independent, which is also another way you could say that is goals do not vary by grade. You could, in theory, say grade does not vary by goals, but there's kind of an inherent natural relationship that goals do not vary by grade. Technically, I wouldn't be upset if you mix them up, but just doesn't really make sense to think about. And so for me, I would be happy if you just said grade and goals are independent, right? A question specific version of the null hypothesis on your formula sheet. I'll say here, be sure to use, question specific variable names. So you've got the prompt on your formula sheet, but then I want you to figure out, okay, well, what would that mean in this scenario, right? Then the alternative hypothesis is just going to be the flip side of that, where grade and goals are dependent. Or if you prefer, are not independent. That's saying the same thing, right? Which means that goals vary by grade, if you prefer that way. But again, all I'm looking for is something like this. You don't have to elaborate. Now, step 2, I call it do the test. Really, I mean calculate the test statistic, but it just doesn't sound as catchy. Do the test. Do the do. Chi-squared at some degrees of freedom, right? On your formula sheet, I have little subscripts. If you don't like the subscripts, they're just saying, hey, for each cell, you have to match the cells up. Okay? So you can drop them if you want. But you take the observed minus the expected, you square it and divide it by the expected value. And as we've already seen on your formula sheet, the degrees of freedom is they use R for the number of rows, and C is the number of columns. R minus 1 times C minus 1. And this K is just do it for all the cells. So the number of cells. As you've noticed, but there's a note here, we do calculate the degrees of freedom differently for one-way or two-way tables. Now, I want to clarify that a one-way table is what we saw in the chi-squared goodness of fit test. Right? We had, the die faces 1, 2, 3, 4, 5, 6, right? And so that's a one-way table because there's not another variable up top, right? We just had the counts. And the two-way tables, which is the chi-squared test of independence, or that's what we use, or we call it a contingency table. The p-value, which in theory is your step 3, right, is the area under the chi-squared at some degrees of freedom curve above the calculated test statistic. So we saw this generic chi-squared distribution might look like this. And if we calculate, I'll do a little axis here. If we calculate our chi-squared, then this would be the p-value. And it's a bummer because you guys are all so well trained now about the one-sided, two-sided, but for our chi-squareds, there's only one side, right? And so we don't even talk about it. We just call it the p-value. Okay. Besides the null and alternative hypotheses, these were just the generic steps, right? And so here, step 2 and step 3. Find the p-value. Oh, that should be a 3. Oh. but let's go ahead and actually do it. Or I might, yeah, we're not actually going to do it because it's a lot of math, but I do want to show how it works. So what we need to do, since we've stated our null and alternative hypotheses, now let's go ahead and find the expected counts, right? We need them in order to check our conditions. And instead of using the slide, I'm just going to add a page. I think we're better off. So we'll start here. Step 0, check the conditions. We need independence. Now we're doing a test for independence, but context tells me that what I'm testing for is whether these two variables are independent of each other, right? And what we mean by the independence here is that each outcome, right, within the variables has to be independent of the other outcomes. Okay? And so for contingency tables, as long as the data was randomly sampled, right, we just need to make sure that all the categories are disjoint. So for contingency tables, as long as the data was randomly sampled, which we usually assume was randomly sampled, we just need to make sure outcomes of each variable are disjoint. In this example, I don't think it said it was a random sample. Students in grades 4 to 6? No, so then what do? We say, I can't do this problem. Save ourselves a ton of work. No, we assume it was randomly sampled. We just say, hey, I'm going to assume that this was randomly sampled. And so we assume students were randomly sampled. All of the outcomes are disjoint. Since a student can only be in one grade, right, 4, 5, or 6, and can only have one most important goal. And can only have one most important goal. That's the independence condition. Now we need our sample size condition checked, which says that each cell has to have an expected count of at least 5. So each cell, bless you, must have an expected count of at least 5. For that, we need to calculate the expected counts. we need to calculate the expected counts. So I'm going to copy. And then just paste it nice and big here. Leaving a little bit of room. Usually what we do is, especially if we're doing it by hand, I have posted an Excel document on Moodle, so I'll show you how to do it in Excel because it's a lot quicker, right? But if you're doing it by hand, usually what we do is we write the expected counts just kind of beside the observed counts because it makes the calculation of each cell, right? The observed minus the expected divided or squared and then divided by the expected. It just makes it a little bit easier, potentially. So what do we need in order to do this? Well, the expected counts are for each cell is the row total times the column total divided by the grand total, which means I need all those totals. So there we go. 63 plus 31 plus 25 is 119. 88 plus 55 plus 33 is 176. And 96 plus 55 plus 32 is 183. If I add those all up, 176 plus 119, I get 478. Well, I need to do the same thing for the columns. 63 plus 88 plus 96 is 247. 31 plus 55 plus 55 again is 141. And 25 plus 33 plus 32 is 90. And what you want to do is I do them all individually and then just make sure that they should add up to 478 again. All right. So plus, I get this 478 is my grand total. So here, this is what we call the grand total on your formula sheet. I'll show the work for the first couple of expected counts, and then I think we'll trust what they tell us. Where is it? There. So they have done it all, and we'll just go ahead and use that. But I just want to show you a couple before we do. So here, the expected count to go with the 63 is going to be 119 times 247 divided by 478. Which, I'm running out of room here, 119 times 247 divided by 478. I get 61.49. And let's just drop it at 2 decimal places. I did see that she just went for whole numbers. Usually I want you to keep about 2 decimal places because these are expected counts. And we've seen that before, right? Expected values don't have to be true possible values. They're just what you would expect if you redid it an infinite number of times. So let's do the expected count to match the 88. Now, one thing that you can check, right, just kind of a gut check, I observed 63 and I'm expecting 61.49. Seems reasonable, right? So far, this 63 that I'm observing seems to be on par with what I would expect to see, right? So that's what we're going to do for each of these cells, but that's what the chi-squared test statistic does for us, right? Is it determines if it's a weird number or not. Now for this 88, right, my row total is 176. My column total is still 247. And my grand total is still 478. Times 247 divided by 478. So the expected count for that cell, I'm expecting 90 point, let's say 95 rounding. So it's tedious, yes, but not hard once you kind of get the hang of it, right? In fact, I usually see a lot of people for a goodness of fit test try to do something like this for your expected counts, but that'll be different, right? That'll be, you want to match your distribution that you think is happening. Okay? And so here I'll make a note. We usually keep approximately 2 decimal places for each expected count. If you're actually doing it by hand, that gets really, really annoying. And so it's tempting to do some rounding, but I urge you not to. But then I saw that she did, so later. So we observed 88. I'm expecting 91-ish, right? Okay, sure, a little bit of wiggle room, right? And so far things are kind of working out and matching what we would expect to see with these totals. Okay. This is all to check to make sure that each cell has to have at least an expected count of 5. And so what we'll do, because we've talked about it already, and here we have the expected counts, and it's way prettier than how I wrote it, right? The expected counts for each of those cells, 6135. What's the expected count for the highlighted cell? That's going to be the row total, 176 times 141, the column total divided by 478. See if I can find that on here. Looks like should be this one. Oh, nice try, Emily. Did I get it? 176 times 141 divided by 478. Yeah. Good. Finally, here are all the expected counts. And so what I'm going to do, and we'll come back here right away, but just for completeness, to finish this condition. So we need to calculate the expected counts. I'm going to paste it in here. And let's see if I can give myself a little bit more room. So these are the expected counts. And when I scan these, none of these are cause for alarm. These are all greater than 5. So these are the expected counts. Expected counts are all greater than 5. So that condition is satisfied. Now I'm gonna go back down there. We snuck in our null and alternative hypotheses. And so now for our step 2, which I'll do here, and let me just go back and make sure that I'm not to lunch here. Haha. I will add it. Step 1, state the hypotheses. We already did it, but I want a non-generic version of the variables are independent. Might be good for practice. The null hypothesis can be that grades and goals are independent. The alternative is that grades and goals are not independent. Or if you prefer to call it dependent, that's fine. I like to have the not in there just to emphasize that we just have the same thing, just negate it. Now, do the test, do the do. From your formula sheet, we calculated all the expected counts. So now for each cell, you want to find the observed minus the expected, then square it, and then divide it by the expected, right? And then add them all up. I'm not going to do them all because that's crazy, but I will do some. Snagging from way down here. So for each cell, and this is where the rounded values are kind of nicer to work with, chi-squared is going to be 63 minus 61 squared, then divided by 61. That's your first cell. And it doesn't matter which way you go. I like to read just left to right down the lines, but if you prefer to go down the columns, it doesn't matter. You're just adding up individual numbers anyways. And so I'm going to move across to 31. How far is it from 35? I square it, divide by 35, plus, ding, 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 ding. I'll pick up here at the very end. So you do it for each cell. 32 minus 34 squared divided by 34. You can see where Excel might be really useful here, right? Just do this thing many times over. In fact, there's an even easier Excel shortcut that I'll show you. But what we find here, and I'm going to bring it up here, even though this is driving me bonkers going around. They did the exact same thing. It's funny. Technically, the sum has already, by adding them, we are taking the sum, so I don't know why that summation was still there, but 63 minus 61, if you just kind of breeze through these and just kind of gut check these numbers, none of these are standing out to me as, oh, that's weird. That's not what I was expecting, right? They're all very, very similar. Okay? And so what that tells me is I wouldn't be surprised if I get quite a small chi-squared test statistic here, right? Because things are kind of behaving how we expect them to. Okay? And that's what we find. So if our chi-squared is 1.3121, right? And like I said, on the test, if I make you do a chi-square test of independence, then I would say the test statistic was found to be 1.3121, right? So you don't have to calculate it, because that's what software is for. And then you just need to know what to do with that, right? What's your conclusion? So once you have your chi-squared, now that is quite small, especially for a chi-squared, but we do need our degrees of freedom in step 3, which is find the p-value or the critical value if you prefer. Right. Since we've introduced it, it's your choice. You can use whichever one you'd like. Either way, you need your degrees of freedom. And I'll grab it from the formula sheet just to emphasize that it is on there. In our case, our degrees of freedom is, I have 3 rows and I have 3 columns. So I have 3 minus 1 times 3 minus 1. Which means I have 2 times 2 degrees of freedom, which means I have 4 degrees of freedom. We're just going to practice with that the tiny chi-square table that's on your formula sheet. Oops, not in your tables. Here. Now what I want to do, and you only have to do one of the methods, right? The p-value approach or the critical value approach. You don't have to do both. Yeah? And so, and even on the test, they would say, find the p-value or the critical value, and it would just be 1 mark for whichever one you do. Okay? So let's do it with the p-value approach here. And let's do it with the critical value approach over here. I'm going to try to do them side by side here. Maybe I'll scooch these over there. For the p-value approach, we determined we have 4 degrees of freedom, which means that, and maybe I'll do this. Copy. Uh-oh. Paste, paste. Add a page. Now I have so many copies of the tiny table. The p-value approach does what? At 4 degrees of freedom, Okay? Remembering that just like the Z on the table, right? The lower bound here is 0, and the area from 0 in the upper tail is 1. Right? That's conceptual, and so I don't put it on the table, but it is there. At the end here, after 14.86, for example, you hit next stop is infinity. What's the tail area at infinity? Well, it's 0. Right? So you've got these kind of invisible bookends on your table. So what we find is when we take our chi-squared, 1.3121, then we want to try to place it on our table, just like we did for Z. But when I try to start here, it starts at 7.78, right? So all I really know is that this chi-squared, which is 1.31, what was it? 21, is somewhere between 0 and 7.78. So it's somewhere between these two values. That's okay. What that tells me is that the p-value is somewhere between 0.1 and 1, quite large. Right? So it's somewhere between 0.1 and 1. So now I have a p-value. From the p-value, I can draw my conclusion, right? If my p-value is less than the alpha level, we weren't given an alpha level, so we'll use 0.05. Then I have enough evidence to reject H0, but in this case, it's not less than 0.05, right? If it's wedged somewhere between 0.1 and 1, it's bigger than 0.5 or 0.05. So then I don't have enough evidence to reject H0. For the critical value approach, what would you do? You would say, well, I'm going to force my alpha level to be 0.05 because that's what we're using. And then we're going to map down here and say, okay, in order for the p-value to be less than 0.05, my chi-squared would need to be bigger than 9.49, which is why we call it a critical value. And so here, at alpha equal to 0.05, the chi-squared critical is 9.49. I'll do the side-by-side conclusions as well, because it depends. If you use the p-value approach, then of course you need to compare the p-value to the alpha level. Or if you use the critical value approach, then you need to compare your calculated chi-squared, 1.3121, to 9.49, right? Because we haven't spent a lot of time with the critical value approach, I just want to draw it out for you. It says that at a chi-squared of 9.49, then this area is less than 0.05, which means you would reject H0. Okay? Not up until that point. Okay? We found our chi-squared was somewhere here, 1.3121, which means I don't reject H0, right? But you want to compare that calculated chi-squared to the critical value. Step 4, the conclusion. I'll keep going with the p-value approach, critical value approach, split, because it depends. Oh. Sorry.
What happens if you got something super close, like 9.47?
Then so you use it as a hard and fast rule, but you'd also make a note of it, saying, "Hey, it was close to being significant," and it kind of depends on if the stakes are high, right? If you're like, well, I was this close, right, to finding a significant result, and so that is a finding as well, right? And so because we're just arbitrarily picking 0.05, right? And so, but that's also a reason why we fix the alpha level before we start, because it's so tempting to go fishing and say, well, what if I just change the alpha level to be 0.1? So usually in papers and stuff like that, which it happens all the time, if you find something really close, right, then you would say it was not significant at our predetermined alpha level of 0.05, but it would be considered significant at an alpha level of 0.1, for example, right? And so you do want to kind of prod people in that direction still. Nice. Same thing with the p-value. If you get a p-value of 0.051, right, then that's really close, right? And so in this course, we use it as kind of a hard line, but in real life, you would be flexible, because you would know what the cost of rejecting H naught is versus not rejecting H naught, right? There's usually some sort of cost associated, not just financial, but maybe time or just kind of materials or whatever. So it's really more of a, we use it as a hard rule, right? Because it's easier that way. But in life, it shouldn't be. You should be a little bit flexible. Your conclusion for the p-value approach reads like this. Since the p-value is between 0.1 and 1, right? So again, just highlight all the things that you've already worked hard for, right? You found what the p-value is. So then you should tell me in your conclusion, right, what it is. So since the p-value is between 0.1 and 1, it is not less than our assumed alpha level of 0.05, which means we do not have enough evidence to reject H naught, which means we do not have enough evidence to reject H naught. If we don't have enough evidence to reject H naught, if we go back to our null hypothesis, then this is our conclusion. Grades and goals are independent. Right? Therefore, we find that grades and goals are independent. Or you can do some fancier version of that, but therefore, we find grades and goals are independent. If you use the critical value, then your conclusion has to include the critical value approach instead, right? So you need to adjust it. Now, I want to highlight just again, you only need to pick one. Pick one. If you don't like the critical value approach because it's new or whatever, right? Don't use it. You don't have to. Same thing for your conclusion, right? Whichever one you picked, do the matching one. So with the critical value, right, then we have this idea that, okay, if my chi-squared, my calculated chi-squared is bigger than my critical value, then I have enough evidence to reject H naught. Yeah? But in our case, since our calculated chi-squared, and maybe I'll put it on the next line, chi-squared is 1.3121, is not greater than the critical value, is not greater than the chi-squared critical, which is 9.49 at an assumed alpha level of 0.05, at an assumed alpha level of 0.05. We do not have enough evidence to reject H naught. Now notice, at this point, we just kind of pick up and have the same conclusion either way. Of course, they should match, right? And so, since our calculated credit is not greater than our critical value and assumed alpha level of 0.05, we do not have enough evidence to reject H naught. Therefore, we find grades and goals are independent. Same conclusion, of course. Oh. Okay. Nice. It's a full question. Of course, they've done it nice and neatly here, where we ended up. We snagged this, right? We found our chi-squared. We didn't even calculate it because yikes. Needed our degrees of freedom, and then our p-value, which was our step 3. Now notice the slides don't even introduce the critical value approach, right? We just stick with the p-value, but now you've seen both. And we've already found the p-value. They use a bigger table than us. And so this uses the table, the bigger table from the slides last day. But I'll just say see above, but see our work using our table, our mini table. Which is what you'll have. And then we have our conclusion. Okay, good, great. Which we did together, but here it is typed up nicely. Because I could tell that it was going to be too quick. I have another example that I just want to work through, but I want to show you the Excel spreadsheet that I posted on Moodle as well. Okay. So a made up example, but kind of fun. Clearly, I made it up around Easter because it's about mini eggs, Cadbury mini eggs, I guess. I probably could have found some on sale, but probably should be Halloween candies next time. A researcher wants to examine the distribution of the colors of mini eggs from 3 different countries: Canada, Australia, and Britain. C, A, B for simplicity. So they collect a random sample from each country and the results are summarized below. You might know that mini eggs tend to come in 4 colors: pink, yellow, green, or blue, which conveniently all start with different letters. Nice. And we found these observed counts. For some reason, the sample size for Britain was huge, whereas Canada and Australia were kind of more normal, right? And so that's okay. This will be taken care of in our expected counts as well, right? So it's not going to blow things up, okay? Which is the reason I did it. Okay? Now we want to know, is there evidence that the distribution of mini egg colors is dependent on the country where we purchase them? Okay? So I found the expected counts. Okay? So I've got them hidden down there. Okay? But first thing we want to do is we want to check our conditions, right? And so is there evidence? Well, that's where you have a deep sigh and you say, oh, that's a hypothesis test. It being out of 7 marks is usually kind of a dead giveaway too, but usually around 7 marks or so. So is there evidence that the distribution of mini egg colors is dependent on the country where we purchase them? So I have a contingency table, right? Hey, contingency table here. And if I want to talk about dependence versus independence, then I need to do a chi-squared test of independence. Okay? So let's start with step 0. Check the conditions. For chi-squareds, that also involves calculating the expected counts, right? So independence. We were told that they collected a random sample from each country. Okay? And each of these countries are disjoint and each of the colors are disjoint, right? And so all the outcomes in each variable are disjoint. Okay? Or rather, what should we say? We assume that a mini egg can only be one color, right? Obviously, there are kind of manufacturing faults, but then you would probably just pick a predominant color and put it in that category, right? Or just eat it and forget about it. Move on. Only use the ones that can fit into one of those 4 colors. So we are told samples were randomly selected, so that's good. We assume a mini egg can only be one color. So disjoint outcomes. And a mini egg can only come from one country in our sample, right? and countries are disjoint. Well, so that's the independence condition. The sample size condition we need our expected counts. You can try it, right? First one would be 91 times 87 divided by 680, right? And then let's try this one because we haven't really done this one. What about 91 times 84 divided by 680, right? Tedious, but not hard. That's like my catchphrase, I guess. I make you do all these tedious things, but they're not hard. I'll zip these up so that we have, I undid too much. Uh-oh. Let me start over here. I wanted to put it here. Once you have all these, notice I've kept 2 decimal places. Of course, if you're using Excel, then you can reference the cells, right? And kind of drag and drop and kind of make it a little bit more efficient. Okay? But I've kept 2 decimal places just for good measure. And when I cruise through these expected counts, then I see that all of them are bigger than 5, so that's good. That will be the case, but we need to know that we need to check that. We see all expected counts are larger than 5, which is good. You can also get a good idea of if things are behaving as you would expect them to, right? And so I kind of struggle with this 32 to 25-ish, right? 15 to 25-ish, kind of same problem. So we'll see if those differences are large enough to be considered kind of a red flag for us. Okay? So step 1, now that we've checked our conditions, step 1, state our hypotheses. Oops. Step 1, state the hypotheses. In general, right, from your formula sheet, the null hypothesis is just that these 2 variables are independent, right? We want to be more question specific. And so the null hypothesis is that the color distribution and country of purchase are independent. Something like that, right? The colors of the mini eggs, right, is independent of the country of purchase. Or if you prefer, although, is there evidence that the distribution of mini egg colors is dependent on the country where we purchase them? You could rephrase this as they are not dependent, right? They're independent. So then you could say the null hypothesis is that the distribution of mini egg colors is independent of the country where we purchase them, which is basically what I said, kind of in shorthand. All right. Our alternative is going to be the flip side of that. The color distribution, and country of purchase are not independent. Or if you prefer to match the question, you could say dependent. That's fine. Okay. Now, step 2. And you can do it, and I'll move it down one. Do the test. Calculate the test statistic. We will use Excel. The problem with Excel is it still wants to know what the expected counts are. And for some reason it can't, they haven't figured out how to build that in, even though I personally feel like I should be able to just feed it this, and it should just be able to calculate my totals and find the expected counts. But for some reason, it's just not there yet. Okay? So on Moodle, I posted this document, and it looks a little something like this. Okay? Now, I don't have a pointer in here, so what I'm going to do is just screenshot this so I can point around. And then I'll jump in here when we need to know what's actually going on. I'll start us off over here. These are the observed counts that we were given, right? And down below, in the same format, right, matching format, I have the expected counts. Okay? And so here they are, or another option. For some reason, it doesn't like it being in a table sometimes. So then what I've done is just listed all the observed counts and next to it, the respective expected count. Okay, making it look like a goodness of fit test, but it's not, right? Behaves the same way, but it's how we found the expected counts is different, right? And then next to it, I found the observed minus the expected, and I squared it, divided by the expected, which is easy enough to do, right? As long as you do it, make sure you pay attention to the first cell, and then you can just send it down, right? Then our chi-squared is going to be the sum of all these values here, right? Then for the p-value, I use the chi-squared dot dist, I think. Let me go in there to see. This is where I needed it. So the chi-squared, and this is why I gave you the chi-squared, the Excel sheet, right? So that you can poke around in there and see how I did it. Notice that the expected counts are just hard-coded. So I didn't do anything fancy and try to reference the cells or anything. But so these are just hard-coded, whereas these are calculated. Let's see if I can, doesn't seem like I can zoom in, sorry. So if you can't see that bar, you'll have to play around on your own. But the chi-squared is just the sum of all those squared deviations. Then the p-value uses, oh, that's right, the chi-squared dot dist dot right-tailed, because you never really want the left-tailed for the chi-squared, so you always want the right tail. Okay? It wants what the chi-squared value is, and it wants to know what your degrees of freedom are. Okay? So we do need to find our degrees of freedom. And since we're using software, we can do that. The p-value is actually in step 3, find the p-value. sorry, the degrees of freedom is in step 3, find the p-value. The degrees of freedom is the number of rows minus 1 times the number of columns minus 1. We have 1, 2, 3, 4 rows and 3 columns, which means I have 3 times 2 degrees of freedom, which is too big for our table, but not too big for Excel, right? And so luckily we're using Excel here. And so that's where that comma 6 came from, is the degrees of freedom, right? Another option that I wanted to show you is just using, oh, now I can zoom in here. Oh, just not on the bar up top. Just using the observed counts and the expected counts. You can use something called the chi-squared dot test, right? Where, let's see if it'll do it. I was hoping it would do that highlighty thing, you know, where it's, you double tap it and it highlights where it's grabbing stuff from. It's not doing that, so, well. But it needs the cells with the observed counts, right? So F2 to F to H5, right? So from 7 to 121, so that whole observed count area, and then the expected counts, and then it just does everything for you. Huh? And it produces what? It produces the p-value, which means it doesn't give you the test statistic, right? But you know how to find that if you need it. Usually we just need the p-value to draw our conclusion, right? The test statistic is just a stop on our way to the p-value. And so here, this was equal to chi-squared dot test of the observed cells, so just highlighted, and the expected cells highlighted. I think it was F2 to, I guess I can do it properly. F2 to H5. And make this arrow a little bit longer. F8 to H11. Oops. The chi-squared dot test only produces the p-value, which is usually what you want anyways, right? But if you want the chi-squared test statistic, right, then you would want to use kind of this method where you kind of do it manually, in my opinion. Right? This is still manual, even though I'm using Excel, I know. So either way, we find that the p-value, and I should highlight that this one is using chi-squared dot dist dot right tail of the chi-squared that you found, which is in C14, and with 6 degrees of freedom from here. Notice that the chi-squared dot test was able, for some reason, to find the degrees of freedom in the background, not the expected counts. It's weird. Anyways, I've got beef, I guess. But either way, using software, we find the p-value. Oops. is equal to something small, 0.00030, I think 1, 2, 3, 7, 8, 2, 9, 1, 8. Why not? Or just 7, 8, 3. Depending on which way you found your p-value, right? You might get more or less decimal places. That's okay. You can always ask for more. Since we have our p-value, I'm not going to bother with the critical value, right? Because the p-value is kind of the more kind of common approach that we use anyways. So then step 4, your conclusion. This is a very small p-value, right? And so since our p-value of 0.0000783 is less than our assumed alpha level of 0.05, we have enough evidence to reject H0. We have enough evidence to reject H0. If I'm rejecting it, then I'll drag HA into it and say in favor of HA. But technically correct if you just ended it there. Reject H0 in favor of HA. Therefore, going back to, okay, my hypotheses. Therefore, I've rejected the null hypothesis in favor of the alternative. So then the color distribution and country of purchase are dependent, right? You can use the alternative hypothesis that we wrote, or if you prefer to just rephrase the question as an answer, that's an option as well. There is evidence that the distribution of mini egg colors is dependent on the country where we purchase them, period. Therefore, this up here, there is evidence that the distribution, can I sneak it in? That the distribution of mini egg colors, I'll delete this, is dependent on the country where we purchase them, period. You could do a deep dive into what the distribution is using a goodness of fit test. What for each country? No, terrible. We're not going to take it that far. But look at us ending early. Unless there are any questions. I should say any questions. We never end early, so it's nice. All right. No questions. Won't see you next week. You'll see me in the video introducing chapter 7. I hope you have a great little mini break